Hello and welcome to the part 2 of the lecture on linear quadratic optimal control in the subject state space approach to control system analysis and design. In the last part of the lecture, we formulated the control problem and we wanted to obtain a relationship for the gain k in the equation u equal to minus kx. We stated the problem. We were heading towards a solution, but we got the famous matrix Riccati equation, and we are yet to derive a proof for the control equation which we just stated in the last part of the lecture. It has been a parade of mathematical equations, and in this part of the lecture also we continue with that parade of complex mathematical equations. I hope there are no typographical errors in the equation while making the slides. In case something is noticed, kindly let me know so that it can be corrected in future. So in the last part of the lecture, we learned formulation of quadratic performance index. We made a statement of the linear quadratic control problem. We derived the matrix Riccati equation and its solution. And it was just stated that the gain k is R inverse B transpose P. P is the solution of the Riccati equation. This expression was given. Here we will prove this expression, and we will also solve an example. While summarizing, we will make a few remarks. So let us proceed ahead. This is something which is taken from the last part of the lecture. In the next slide onwards, we will use short notations: P in place of PTTF, AC in place of ACT, etc. to let the equations and expressions look simple, have simple experience. So we specified this performance integral J, which was a quadratic in state weighted by weighting matrix Q, plus a quadratic in input weighted by the matrix R, and this was written as X transpose at time t, the now time or initial time, multiplied by P again X. This was written, and this part, which is P, is given by this. This is the solution, and this is the Riccati equation, which is satisfied by this solution. Of course, AC is the closed loop system matrix A minus BK. Now we start with this. We do few mathematical manipulations to derive the expression for U. Now if we see the expression for J, which is X transpose PX, of course X is the state of the closed loop system, X transpose PX, then this quadratic will be minimum if P is minimum. It is quite obvious from this expression. So we say that optimal value of P is P hat, optimum value of K is K hat, and of course this P hat and this K hat, they will satisfy the matrix Riccati equation, which was written here, So P hat dot should be equal to AC transpose P hat plus P hat into AC plus K hat transpose R K hat plus Q. This is written here. This is written here. So in place of P we have P hat, in place of K we have K hat, and AC is A minus BK, so this expression becomes this: P hat dot equal to P hat A minus BK plus A transpose minus K hat transpose B transpose, the transpose of whole, into P plus K transpose RK Q. We can rewrite this as this. Now the non-optimum values of K and P can be expressed as optimum value plus deviation from that. Optimum value of P plus deviation from that. So the K is K hat plus L and P is P hat plus S. Then that J becomes, it was X transpose Px, it becomes X transpose P hat plus S, because P is P hat plus S, and it can be opened as X transpose P hat X plus X transpose Sx. Proceeding further, we know this expression, it was there in the last slide I think, or the previous to the last slide. So what we do in place of P everywhere, we substitute P hat plus S, and in place of K we substitute K hat plus L. Then this equation becomes this equation. Simply a substitution of P hat plus S in place of P and K hat plus L in place of K gives to this. We do the mathematical manipulations and then we get from this, we get this S dot. Of course what we have done is that from this, after simplifying, opening these various product terms, we have subtracted from it P hat, which was there in the previous slide. Let me go back and show to you one slide back, one more slide back, one more back. This, we have this expression for P hat, this expression for P hat. So this expression for P hat is subtracted from this expression, leaving the cancellation of terms like P hat dot, P hat, etc., K hat, RK, and so on. And what is left is this one, involving only on the left S dot. And S is deviation in P from the optimum value of P. So S becomes this one, S into this transpose into S, and this. Now because these deviations will be small, so we recognize that, and before that of course this equation is identical to the equation for this P, and for which we had the solution given in terms of a integral. So similarly the solution of S on similar lines can be written like this one. This is very similar to that solution for P which was shown in the first slide of this lecture in the beginning itself. So we have this solution for S, which is the deviation in P, deviation from P hat, the optimal value. And let me go to previous slide, this one. In this one, these are deviations, and there are terms like this, product of deviations. So what is going to happen when j tends to j hat, k tends to k hat, this L will be small, and some terms we can ignore like L transpose RL, and some similar other terms where we have the product of S and then L somewhere, like S B L transpose, like that. The terms coming like this S into B into L, like that, those kind of products. Because S is small, L is small, we can ignore some terms of that kind, and we will be left with only this from this one. This will be given by this, and which will mean, because this and this are same transpose of each other, so which will mean that Rk is B transpose P hat, and from that we get K hat equal to R inverse B transpose P, and this is the solution of control gain in U equal to minus Kx. This is the optimal control giving the optimal input. R inverse B transpose P hat, and P hat is the solution of the matrix Riccati equation that we have seen. So what we do, this expression we substitute in the expression for P hat, which was there in the previous slide. Let me go back and show. This is slide 12. I go to slide 11 and even before that on slide 9. No, even little before that. So here P hat. This is the expression for P hat here. So this P hat, these are this. In this, we are going to substitute that K hat equal to R inverse B transpose P hat. And this will lead to, now I am going forward to slide number 12. This will lead to this equation. In place of K, we have made substitution R inverse B transpose P hat. So that term has become this, which was K transpose, K hat transpose R K hat. It has become P hat B R inverse B transpose P hat, giving this equation. This equation can be solved for P. Of course, a value of Q and R is to be chosen in the beginning, has to be selected. That itself is a little difficult job. It requires experience on the part of the designer to select the Q and R. So once Q and R are selected, those values can be plugged in into this equation to obtain P hat, and then P hat can be substituted in this one to get K, R inverse B transpose P hat. And then we have the gain, we have the equation U equal to minus Kx plus of course R. This is the control law we wanted, and what we are seeing that we selected one integral performance index, which is combination of cost function of state and cost function of input, x transpose qx plus u transpose ru. Q and R are to be specified. Then we get the matrix Riccati equation. We solve the matrix Riccati equation and we get the gain K. And this gain K with this control law, we'll minimize the integral performance index J equal to x transpose qx plus u transpose ru integrated from current time to final time with respect to tau, d tau. So once Q and R are there, matrices A and B are known, then entire effort is to solve for P from this matrix Riccati equation, and obtaining K is then very simple task. So whole effort is in solving for P, and with the availability of computer and software packages to solve for this kind of equations, that is even much easier. So entire effort is essentially in selection of Q and R. Select Q and R with the knowledge of A and B and Q and R, we get P and then we get the K. Now we see a small variant to this. If the upper time limit is infinity and the closed loop system is designed to be stable, then matrix P hat will become constant, and that means P hat dot becomes 0, which is put here in place of P hat. So this is now not a differential equation, this is just an algebraic equation. So when the upper limit of integral is infinity, the matrix Riccati equation reduces to an algebraic Riccati equation. And the characteristics of this equation are that it is a set of n into n plus 1 by 2 coupled scalar quadratic equations. Why only n into n plus 1 by 2 and not n square? Because this P is a symmetric matrix. And so only because of the symmetry, only half of the matrix is to be considered for equations. So we have n into n plus 1 by 2 equations and not n square equations. And these equations can be solved. Of course, the conditions for existence of the solution are that the system should be controllable. Only then the solution will exist, and this Q should be selected so that it is at least positive semi-definite. If it is positive definite, it is even better, but it should at least be positive semi-definite. And R must be positive definite. We saw that its inverse is involved. So R must be positive definite. So if we select a Q which is at least positive semi-definite, AR which is positive definite, and if AB make a controllable pair, then a solution to this equation exists for the symmetric positive definite matrix P hat. And once P hat is known, then K is R inverse B transpose P hat. This is the optimal gain K hat can be obtained. So we take an example which is a second order system. I have taken it from the book by B. Friedland. I have given this reference earlier also. So this example comes from the book authored by Bernard Friedland. It is a second order system which is in controllable canonical form. Of course, it is not important for design of the linear quadratic regulator. So what we do is, we have to obtain a control u equal to minus kx such that we choose this performance integral. x1 square plus u square divided by c square. 1 by c square is the weight to the input, and of course the weight to state only x1 is there. X1 square means that Q matrix is essentially 1 0 0 0, and U transpose RU, there is only one input, so that R is 1 by C square, that is taken. This second order system, with this performance integral to be minimized, and as I explained, we have Q as 1 0 0 0 and R as 1 by C square. So because it is a second order system, the matrix P will be a 2 by 2 matrix, and because it is symmetric, so we have to assume it like this. In place of P21 we have P12 only, because it is a symmetric matrix. So we assume this form of a P, and now we set up the algebraic Riccati equation. So A transpose P will be this, A transpose, this is P, will be this, and PA will be transpose of this, which is this, and P, B, R inverse B transpose P, this is P. Of course this has to be written as P12, I'm sorry for the typographical, this also is P12. So this is P matrix, this is B, this is R inverse, R was 1 by C square, so R inverse is C square, this is B transpose, this is again P or P transpose, so all this evaluator gives this expression. C square P12 square, C square P12 P22, same thing, and C square P22 square. And Q we have seen it was specified in the previous slide. So A transpose P plus PA minus PBR inverse B transpose P plus Q equal to 0. When we set up this, we get this. This is A transpose P, this is PA, this is PBR inverse B transpose P. This minus sign has been absorbed inside, and this is Q, and all this should sum to 0. Now writing term by term, we get 3 equations. So remember it was said n into n plus 1 by 2 equations. So 2 into 3 by 2, 6 by 2 are 3 equations in this case, because n is 2. System is of order 2. So we get 3 equations instead of 4 equations, because P12 and P21 are identical. These are the 3 equations. Now this equation is a quadratic in P12. It will give 2 solutions, and suppose one of them is coming negative, then we cannot accept that, because this equation will give root P12, and if P12 is negative, then root P12 will be a complex number, imaginary number, and so P22 will be a imaginary complex number. We want P only real solution, real and symmetric. Symmetric we have taken care by choosing P itself symmetric in the beginning, but it will be real only if P22 is P12 obtained from this is positive. So out of the 2 solutions of this, we will accept only that solution which is positive for P12. So once we have that, then we get P22 from here, and once P22 is available, P12 is available, then we have P11. And of course that P equal to P11, P12, P22, P12 here again. This should be positive definite. So for this, P11 should be positive. We will get that. P22 should be positive. We will get that. And all entries real. So only those solutions we will accept. So if we do that, we get this, the solution for various elements of P. And then we obtain K as R inverse B transpose P. After evaluating, we will get this expression. This is K1 and this product is K2. So we get K1 and K2 like this. And so the closed loop system matrix A minus BK we will get like this. And if we see the roots of the characteristic polynomial of AC or the eigenvalues of the closed loop system matrix or closed loop system poles, we get these two poles. And that C square, which we have taken as a parameter in the control weighting, remember that J was taken as integral of x1 square plus u square by C square. So this C square, its effect will be evident on the location of the closed loop poles. We can see that if C is very large, so this whole thing will become root C. This C square is larger than omega power 4 and its root gives C, and again that C is larger than omega square, so the whole thing gives a root C, and this will give minus root C, so J root C. So what we'll see that if C is very large, and of course that will mean that control is inexpensive, control is cheap, C squared, that term, it was U square by C square in J. J was this, x1 square plus U square by C square. If C is very large, the weightage to control is 0, nearly 0. And control is inexpensive, and so what we find that these two parts are equal. Of course this one is imaginary, so if we look into the S plane, the roots will be located on plus minus 45 degree. This will be 45 degree, this will be minus, this will be 45 degree too, and the roots will go on this, asymptotic to this. When C is infinity, then they are on this, and at infinity, they are at infinity. So meaning that when the control is cheap, then of course infinite control energy can be put in the system, and we can get almost instantaneous response from the system, very fast response. The bandwidth will be large. This will go, poles are going away and away from the origin. So infinite speed can be obtained. So for the large values of C, meaning that when the control is inexpensive, the design by this linear quadratic regulator design method leads to closed loop poles which are away in the left half S plane from the origin, and also they are located so as to provide the best damping. The other thing is, if C is large, if C is small, meaning that control is costly, some cost. If value of C is very small, then the control is very costly. Then we can analyze these to see that poles become almost minus omega. So I was trying to plot the root locus. The poles will be here minus omega, giving a critically damped system. The two roots become equal, giving a critically damped system. Other thing is that the open loop system itself had the eigenvalues plus minus omega. And what has control design done? For large weightage to the control input, it has retained the stable pole where it was. However, unstable pole it has brought to the same location, or unstable pole has been brought to a mirror location with respect to the imaginary axis. So this is what happens in case of linear quadratic control. The unstable poles are brought in the left half S-plane almost at the mirror location. If of course, if the control weightage is large. If the control weightage is small, then they will be placed very far in the left so that the system response will be fast. This is the characteristics of the design that is obtained by application of linear quadratic regulator approach. Of course, it is demonstrated here by only a second order system, and one can get better feel by solving higher order system or different systems of second order itself, which you should do as an exercise. We summarize and make a few remarks. So we have discussed linear quadratic optimal control, and we see that the control law is similar to that in the pole placement design. However, here the control gain is achieved through minimization of a quadratic performance integral, quadratic performance index, and in the pole placement the K was obtained through selection of closed loop pole locations or coefficients of the characteristic polynomial. So the solution of the problem leads to the feedback gains, and of course Q and R are to be selected. So if we saw while we were discussing the example that if there is difficulty in selecting Q and R, if some state like x1 was given weightage, x2 was given 0 weightage, so the performance index was only x1 square for the state. So we have to have little understanding of the physics of the system. The states which are more important to be regulated, to be controlled, their weightage has to be kept relatively larger compared to the other states, and the states which are less important or very less important will be accordingly assigned a smaller weightage or 0 weightage. Input is that we have to respect the constraint on the input. Accordingly, the weightage of the input has to be selected so that the control will not be driven to saturation and it will obey the linear control law. So that Q and R are to be selected, keeping these things into mind. Of course, their relative values are important, not the absolute values. So if both are large, means both the state weightage is large as well as the control weightage is large, then relatively in comparison to each other, one may not be large compared to the other. They may enjoy almost equal weightage if both are large. So what can be done if the system is complex or if the physics of the system is poorly understood? Then selecting Q and R may be a challenge, not only difficult. So one has to do the design of K, one has to obtain K by selecting different Q and R, so many combinations, maybe at least a dozen or hundreds sometimes combinations. For each combination, do the simulation and from the simulations in the representative scenarios for different kind of inputs and different kind of initial conditions, different kind of scenarios, they select the best or nearly the best optimal design. So that has to be done based on simulation or by better understanding of the physics of the given system. There are other forms of PI in which we had X transpose QX plus U transpose RU dt. This was in G. But sometimes it can contain terms like X transpose M transpose U. This is X one side, other side U. These are X and X are U and U both sides. So this is a different term. So X transpose M transpose U or U transpose MX are also present. This may occur in some kind of designs, and in that case the theory will be applicable. Of course, K expression will change like this. R inverse B transpose P, this alone was there, to that M will be added. Then other form of PI is this. There is a penalty on state at the terminal time, TF. This is X transpose at TF, X at TF through a weighting matrix N. And this is similar to the performance index which was considered. So this is the penalty on the state at the terminal time, final time. This kind of a performance integral is more general. However, its solution is also the same which we obtained. Only the initial condition differs. Earlier we had this, it was 0, and here it will be n. So the solution will start with initial condition n instead of initial condition 0. K will be same which was obtained earlier. This one more remark which I want to make, that I also made at the time of this presenting, telling about the Ackermann's equation and talking about the controllability of large scale systems, systems of higher order. This again, this solution of matrix Riccati equation or algebraic Riccati equation to large scale systems, the systems in which the order is very large, or even the smaller systems in which matrix A has some elements large, some elements small. The ill condition in the system with ill conditioned system matrices and input matrix. There, this Riccati equation may not be easy to solve because of that large numbers and small numbers. That quadratic terms you saw, they were there. I'm going back a few slides just to show the kind of, yeah. So here, this quadratic equation will be ill conditioned, and it may not be easily solved. In case of higher order system, some kind of conditioning needs to be done, or some indirect approach is to be adopted. That is required many times. Then throughout the discussion or throughout the design, you did not observe that whether it is a single input system or whether it is a multi-input system. It is the same method for both single input or multiple input systems. In case of pole placement, we had difference in approach. So this is where this quadratic optimal control scores over the pole placement methods. Thank you very much, and see you again in other lecture, some other lecture.